Well, we're finally here. The last video on introducing gas laws before we get back to some real stoichiometry and start looking at how we apply these and use these new equations for the mole that we've been introduced to in some traditional stoichiometry problems. And do a lot of more maths in class, practicing those. Okay, so let's move on and have a look at this little bit of an expansion on Avogadro's law and what that means for how gases behave in terms of volume. So what we're going to do is introduce an idea of a molar volume of the gas, and what this literally means is the volume, sorry, I can't spell, but we all know that by now, the volume of 1 mole of gas. Okay, so when we're talking about molar volume, we are simply talking about the volume that 1 mole of gas occupies. So we can use our ideal gas equation and have a rearrange for volume, and we can see that we end up with nRT divided by P. So the volume of the gas at a particular pressure and temperature has a fixed value irrespective of the type of the gas that it is, because all that we're doing here is looking at N, which remember relates to the number of particles of the gas, okay, but not what the gas is. So N will be the same irrespective of what the gas is, because if I had 0.5 mole of O2, N is going to be 0.5. If I had 0.5 mole of NH3, it will still be 0.5, which would be 6.02 times 10 to the 23 divided by 2. Okay, so it doesn't matter what the gas is, it will always, at the same temperature and pressure, have the same volume. And that's what Avogadro discovered. Okay, so if we have the same number of particles, then those particles will be colliding in the same way with the sides of a container. Okay, we would have as many collisions per second irrespective of the gas. Okay, so let's have a look at what that means in a little bit more detail. So essentially what this is saying is that if I keep T constant, okay, if I keep P constant, and I've now got N constant, then it flows from that V will be constant. Okay, so what we get from this is that at the same temperature and pressure, for a given volume, it will have exactly the same number of particles in it. Okay, and we can see what that means for helium, ammonia, and oxygen here. The key thing to remember is that mass is not constant. Okay, the amount of mole is constant. Okay, so helium is 4 grams divided by 4 equals 1 mole. Okay, for ammonia, 15 grams divided by 15 grams per mole is equal to 1 mole. O2 is 32 divided by 32 is going to equal 1 mole. So while the number of mole is constant, each of these balloons would have a different mass. Okay, so because the molar mass is different, 1 mole would weigh a different amount for each one. But we would have exactly the same number of particles in each one, which for when we're looking at reactions and how things react is critical, because we're really looking at the number of particles, not the mass. So essentially what this does is get us a new equation for the mole, because if 1 mole of any gas at the same temperature and pressure occupies a fixed volume, known as the molar volume, if we know the volume at a fixed temperature and pressure that 1 mole would occupy, we can work out the number of mole. If you have a look here, we see this value here, 22.4. Okay, and for us, Vm is going to equal 22.4 under the standard temperature and pressure that we're going to look at. Okay, so STP. And you can see that this is 1 atmosphere, 273 Kelvin, 1 mole of gas, different masses, all have the same volume. You'll notice temperature is in Kelvin. In this case, pressure is in atmospheres, but really we just need the pressure to be constant. We need to say that the gas is at a constant temperature and pressure in the question. and we know they'll have the same volume. If we want to know exactly what that volume is, it needs to have been measured at that temperature and pressure. Thankfully for us, that's exactly what a bunch of scientists did, and they defined a set of common parameters. They called this standard temperature and pressure. Okay, STP, standard temperature and pressure. So this is a set of conditions under which a whole bunch of things were measured, okay, and are used as reliable values for us to be able to compare against. So for us, for IB, we largely use STP. You can also come up with SLC, which is standard laboratory conditions, which is actually 25 degrees C, which is 298 Kelvin, and 100 kilopascals, or 1 atmosphere. Okay, this is just at the temperature, standard laboratory conditions, temperature that us as human beings can live under, because otherwise if we had to do all our experiments at 0 degrees C, people would be pretty unhappy. Okay, so there is a value for this. It's not used very much in the IB. When it is given to you in the question. It's approximately around 24.5 decimeters cubed for this one. Okay, but for the value of VM at STP that is given in your data booklet, it's 22.4 decimeters per cubed, decimeters cubed. So if we look at this, essentially everything's constant. Our formula simplifies down to if P and V are, we're just looking at V, okay, and then we've got a constant, temperature's constant. It simplifies down to the molar volume of a gas, and this is 22.4. So it gives us a new formula for the mole. Hooray, another one for us to learn, which is the number of mole of a gas. Okay, these only work for a gas. It doesn't work for anything else. Is equal to the volume of the gas divided by the molar volume of the gas. Okay, and remembering that this is when the gases is at STP. Okay, so the volume will be constant if the volume will have the same value for the same value of mole at constant temperature and pressure. Okay, that's one relationship that we look at. If we set that temperature and pressure constant at standard STP, that is 0 degrees C and 100 kilopascals, or 273 Kelvin, we can use this one here, only at STP, remembering that STP is 273 Kelvin and 100 kilopascals. Okay, if these conditions are met, then we can use this this here, and this value is 22.4. Okay, so let's have a look. Now we have a value to be able to measure against to see how well our gases meet an ideal gas. So if we look at the actual measured volume, okay, of gases at 0 degrees C and 100 kilopascals, we can see that hydrogen is 22.43, which puts it within pretty good range. Neon 22.44, oxygen 22.39, nitrogen 22.40. So these are all a very good approximation. Carbon dioxide 22.26 and ammonia 22.29. So here we're starting to see a greater deviation, as we would expect. Okay, I wonder if you can explain why carbon dioxide would be a little bit different, even though it's non-polar. Have a go and think about that one. So essentially what we've done is defined a new equation for the mole. Okay, so if N is equal to V on Vm, for those of you who like the triangle, it's set up here. But essentially what we're saying is that 1 mole of gas at 273 Kelvin and 100 kilopascals will always have a volume of 22.4 decimeters cubed. If these conditions don't apply, 273 Kelvin and 100 kilopascals of pressure, then we cannot use this equation, okay? We need to use our ideal gas equation or our gas laws if we have initial and final conditions in order to solve the problem. But if these conditions do apply, then we move away from a 5-variable equation into something much simpler, and we can just use this N equals V on Vm. So let's have a look at how that will look in some questions. So we've been asked what volume would 1.2 mole of neon at negative 20 degrees C and 62 kilopascals occupy at STP. So in this case, what are we going to use? We've got 1.2 mole, a temperature and a pressure, and we've been asked what will it occupy at STP. Okay, so we are changing it to STP. So we could use P1V1 over T1N1 is equal to, P2V2 over T2N2. But that's going to be a lot of substituting in. If we're at STP, then irrespective of what the volume is, N is going to equal V on Vm. We actually want to solve for V, so we're going to get V is equal to N times Vm in this case. So we've got 1.20 multiplied by 22.4. Go back to our original problem. Sorry about that, it's been really bad. 1.2 times 22.4, so we would expect it to occupy 26.88 decimeters cubed. Okay, looking at our significant figures, 3, when we convert this to Kelvin, it would be 293, and in this case, we're not actually using these in our calculation, so we can ignore those. This one is the only one we used in our calculation, and 3 here, so to 3 significant figures, 26.9 decimeters cubed. It's my final answer. Okay, next one. What volume of gas would 2.15 mole of oxygen occupy at STP? So again, V is equal to N times Vm, because I'm at STP. Doesn't matter what this is. So I get 2.15 multiplied by 22.4 equals, and I get 48.16 decimeters cubed. And there we go. In this case, taking it to 3 significant figures again. Okay, so we're going to go 48.16, well, that's going to round up, 0.2 decimeters cubed. Final answer. Okay, so we can use this in stoichiometry problems, and this is a fairly simple stoichiometry problem, and we'll have a quick look at that. But essentially what we're going to do, what volume of hydrogen will react with 22.4 litres of oxygen to form water? All volumes are measured at STP. So this is telling me, think about something, it's STP, I can use this one. Okay. So let's have a look. We need to work out what the equation is first. So we've been told we've got hydrogen gas plus oxygen gas is going to H2O, and this will be a liquid, so we're going to ignore it out of our, we can't do anything with this in terms of using our gas laws. Okay, we would need to use probably our mass laws in order to do that. But these are gases. We know we're at STP. I do need to balance my equation, so I can see here I need 2 of these. And now we've asked what volume of hydrogen will react with 22.4 litres of oxygen to form water. Okay, well, what we can see here, and one of the beautiful things about the relationship about gases having the same volume irrespective of the nature of them are, what we're saying here is that 2 volumes of this will react with 1 volume of this. Okay, so if my 1 volume of this is 22.4, I want to solve for x, so x is going to be equal to 2 times 22.4, which is 44.8 decimeters cubed. So I will require 44.8 decimeters cubed of hydrogen in order to react with that amount of oxygen. Okay, or what we want, 2 over 1 of what we got is 2, and then just apply that to my volume because it's proportional to my number of mole. So this relationship using volumes instead of mole only works for gases at STP. Only works for gases at STP. Okay. So just a quick summary of where we are with all the new equations and everything that we've done. We've defined an ideal gas as a gas that obeys Boyle's law, Charles' law, Avogadro's law, and the 5 assumptions of ideal gas behavior. From that, we got our ideal gas law, which is PV equals nRT, and our combined gas law equation P1V1 over N1T1 is equal to P2V2 over N2T2. Okay, we have said that the volume, pressure, temperature, and number of mole of a gas are the variables that influence its behavior, and that gases exhibit the unique property that at a set pressure and temperature, the volume is directly proportional to the number of mole. Okay, and then we defined molar volume as being the volume of 1 mole, and at STP we know that volume is 22.4 decimeters cubed. Hopefully you are at the point where you've got some good notes put together for these and you have finished the first 2 sets of note packs. There will be new note packs put up for ideal gas law as well, and we will practice a lot of questions with these until you are comfortable and do a few more experiments as well. See you in class.